Hello, YouTube. My name is Nick Grijalva, and this is PHYS 2212 Lab 1 on charged tapes. The purpose of this lab is to demonstrate and observe how charged particles interact with each other. In our current lab, our system, which is tape B, is being levitated by tape A using electric repulsion. The surroundings in our lab are tape A and the force of gravity applied by Earth on both tapes, specifically on tape B. The relevant laws and principles in this lab are the force of gravity, mg, which we can cleverly equate using Newton's second law, where each applied force is an equal and opposite reaction, with Coulomb's law for the force of electricity. The force of gravity is being resisted by the electric force, and that is what allows our tape to be levitated. The measurements we observed during our physical lab are that our U tapes, have the dimensions of 20 centimeters by 1 centimeter in terms of surface area. And we were given the approximation that there's 1 gram per meter of mass, which gives us, in our case, zero point 0.2 grams of mass for our entire U tape, each individual one. And we approximated our distance when the tape began levitating at 1 centimeter. Well, that actually ends up being a very rough approximation. And so going into our physics calculations for the real world model, we can plug in to mg our mass for each U tape and solve for the applied force of gravity at any time. And then we can equate that with our formula for electric force, and we can rearrange our Coulomb's equation and gravity equation to solve for the relative charge for each U tape. And then using our electron constant, we can solve for the number of. And then by using our surface area that we got from our observations and an approximation that every atom has a length of 1e negative 10 for each individual atom, we can solve for our total number of atoms and then use our total electron calculation to solve for the ratio of discharged atoms during the interaction. And so here's an overview of our code. We set up our physical constants, lengths, and the separation that we got during our actual lab. And then we can apply our rearranged Coulomb's equation here, and for the total number of atoms, and then we can solve for the ratio. And then finally, we can apply our electric field using the Coulomb's equation by assuming that it's a point charge. And here are our results. The numbers are actually relatively similar between the two. The force is equal. That's likely because the force of the electric force ends up being equal with the force of gravity in both equations. And then there is some inconsistency between electrons discharged, but they're in the same magnitude, which is good enough, I'd say, in this scale. And our electron discharge ratios are also quite similar. Let's go over some questions. We made an observation earlier that our charge tape is positively charged because it was able to attract to a negatively charged plastic object. What would happen if we were to make that positive charge equal a negative charge instead? How would that affect the outcomes of this lab? And so the charged tapes would still repel because now they are both charged negatively, and these two things repel. And instead, the tape would repel negatively charged objects like the plastic we tested. Another salient question is why it even is important to handle the tapes so carefully as we had to during the lab. Positively charged tapes are in a deficit of electrons, and when they come in contact with other charged objects or even neutral objects, they will gain electrons from them and become more neutral, thus losing their charge behavior. Here are the assumptions we made for our code. There's no air resistance, each long tape becomes a point charge in our code, and every U tape has similar charge and similar atom arrangement and charge arrangement. There were some obvious margins for error during this lab. The tape handling could cause massive fluctuations in the charge and the behavior of the tapes. It's difficult to measure the tapes accurately, even though we had rulers that could cause all sorts of distortions. The air resistance applied there actually isn't irrelevant at this size and this weight and this shape of the tape. It's pretty malleable. And there's some errors in calculation that I might have made on my own that are just because the objects are not really that intuitive at this scale. Like 1.92 e negative 3 newtons for the force. There's no way I can know that that's egregious or not compared to like being hit by 10 billion newtons for like a train or something. That's something I can tell. But this thing, it's a bit different, and I think this unit will definitely be a nice challenge for all of us. Thank you.